We can also use electronic effects to look at the strength of weak bases. Here I've drawn up two weak bases that are based on nitrogen, and you'll notice that there's a lone pair for each, right up there. Now, if we recall, the definition of a Lewis base is the ability for that base to donate an electron pair. So this electron pair needs to be able to leave or be available to react with an acid. Same thing over here. This electron pair should be available to react with an acid. Now, in the case of dimethyl amine, which is the name of this because there's two methyl groups and it's a nitrogen-based compound, so an amine, these are electron donating groups. So these feed in electron density into the nitrogen. That will allow this electron pair to be more available to an acid that would come by to react with it. Whereas over here we have a fluorine that's attached to the nitrogen. Now fluorines are electronegative and therefore they pull electron density towards them. So this lone pair will be less available. And we could draw that simply by doing this. Here we've drawn the electron pair. And then over here, let's do the same thing. But now we have a fluorine on the nitrogen. And in that case, the electron pair will be much smaller. The orbital will be a lot smaller. Why? Because, again, the electron density is being pulled towards the fluorine. Whereas in this case, electron density is being fed in from these electron donating groups. Carbon-hydrogen groups tend to donate electrons. Fluorine groups and other electronegative groups tend to pull electron density away. Other electron withdrawing groups can be an NO2 group, like a nitro group. Other halogens, like a chlorine, some of these are also electron withdrawing. You'll just have to examine, cyanide, that's another one that's electron withdrawing. Generally, when we look at electron donating groups, it's carbon-hydrogen things. So, again, we're thinking about how available is this electron pair to be given away. If it's a larger orbital, this electron pair is easier for an acid to get to. And if I have a larger Lewis acid, such as bromine trifluoride, boron trifluoride, like this, that can react with this nitrogen base. Now, sometimes people will draw a little arrow here to indicate that both of the electrons for this bond in between the nitrogen and the boron came from the nitrogen. And that's called a coordinate covalent bond, which again is just another name for a bond that's being made between something that has donated both electrons towards the bond and something that's accepting both electrons. These are also called adducts. And that's just the name of something, the product of a Lewis acid reacting with a Lewis base. This is a Lewis acid because the electron density is being pulled away from the boron, which is already an electron deficient atom, right? There's only 6 electrons here, whereas it could go up to 8 to form the octet. But we can make it stronger by stabilizing it with the fluorines, because boron is okay with less than an octet. Over here, you'll notice that since this electron cloud is a lot smaller, it will be harder for it to interact with the Lewis acid. And if the Lewis acid had some very large groups on it, it may even block the Lewis base from reacting with it. And it could be very difficult for that electron pair to get into the place where it needs to react with the acid. However, with a larger electron cloud, it's much easier because it will not be hindered in that way. So that's a little bit about the strength of weak bases.